This unit is called thermochemistry, and it's going to involve different types of energy. So let's start with what energy is. It's the capacity to do work or to produce heat. So there are two parts of this, the work part of it and the heat part of it. Work is considered to be a force acting over a distance. Usually that means moving an object. And heat is going to be a transfer of energy. And the units for that are J or kJ for kilojoules, which is different from temperature. And we're going to talk about that in just a minute. We do have to follow the law of conservation of energy here, which is very similar to the law of conservation of mass. So energy cannot be created or destroyed, but you can change it from one form to another. So the potential energy in terms of chemistry is going to be talking about the energy stored in the bonds, and kinetic energy is the motion of an object. The equation for kinetic energy is 1/2 mv squared, and this is on your reference packet, which means that there's a good chance you'll be asked about it. And there's some homework problems that you're going to do that involve this equation too, that ask you to calculate the kinetic energy of the particles. So first of all, in this equation, m stands for the mass. So the bigger the mass, the more it's going to affect the kinetic energy. And then v is the velocity. Now the thing is, you usually want the energy unit to be in joules, the capital J, and 1 joule is equal to, this is a really good conversion to just be familiar with, you'll use this a lot, it's equal to 1 kilogram meters squared per second squared. So the thing about your units is that if you can get your mass, this m right here, if you can get that into kilograms, and if you can get your velocity into meters per second, then when you calculate, when you plug those in, your final unit will be in joules. So be careful with your units when you plug those in. All right, like I said, we need to talk about heat versus temperature because a lot of students have trouble identifying the differences between these. Temperature, the definition is the average kinetic energy of particles. So we're talking about how fast the particles are moving. Average is because not every particle is moving at the same speed. We can measure this with a thermometer, and we usually use degrees Celsius or Kelvin, and this is going to determine which direction the heat goes. So anytime that you put two things next to each other that are at different temperatures, heat will be exchanged. Heat will leave the thing that's at a higher temperature and go toward the thing at a lower temperature until the two are at the same temperature. Not necessarily halfway between them, but because there's some other factors that are involved, but it will have a transfer of energy. So for example, when you hold an ice cube on your hand, I know it feels like coldness is going into your hand, but really what's happening is that because your hand is at a hotter temperature, heat is going to go from your hand into the ice cube. And when heat leaves your body, the sensation that you feel is coldness. Coldness is not really a thing. It's more of it's lack of heat, but that's what you feel when you lose that heat to the ice cube. So temperature is a measure of that motion of the particles. Heat is a transfer of energy. So we can't just go to a lab bench and say how much heat is in this beaker, but what we can say is what is the temperature of the beaker, and we can say how much heat is leaving the beaker or how much heat is going into the beaker. So you have to calculate this amount of heat energy. You can't just measure it. And this is going to depend on the temperature change. So the bigger the temperature change, the more heat is going to be involved. It also depends on how much stuff you have, and the fancy word for that is mass. So the mass of the object and how easily, I don't know why the line went down here, how easily that substance absorbs or releases energy, and that's called specific heat. And we'll get to that a little bit later too. So there are lots of factors that depend on how much heat is involved. And we really care a lot about this energy and this heat because that's how we function in terms of like your car engine. You need to make sure that that chemical reaction is producing enough energy to actually make your car go. So we use these all the time in our real life. Okay, the next thing is a state function, and this is a state function doesn't matter how you got to that information. So for example, if you have a balloon and I say what is the volume of the balloon, it doesn't really matter whether you started with an empty balloon and blew it up or whether you started with a huge balloon and some of the air has been lost. So we don't really care how we got to that, we just care what is the volume. But heat and work are not state functions. So what that means is that we do care the direction that they're going. And we indicate that with a positive or a negative sign. So you have to get out of your head the idea that positives and negatives have to do with the number line, because in chemistry, they don't always mean that. I know they do in math, but in chemistry, the positive and negative is just telling you which direction that is the heat or the work is going. So positive means that heat is going into the system, so that would be an endothermic process. or that work is being done on the system. So if you have a balloon and you're pushing on it and you're decreasing the volume, that means you're doing work on the balloon. So just think of positive as going in. Negative means that heat is leaving the system, so it's going to feel hot when you touch it because heat is going out. Or work is being done on the surroundings, which means if the balloon is expanding, it's kind of like the balloon is pushing on the air around it, so it's doing work on the surroundings. The system would be like the balloon, and the surroundings are the things around the balloon. You've heard these words a lot, endothermic versus exothermic. So these can apply to both reactions or to physical changes, like a phase change. So solid to liquid would be endothermic. So gas to liquid would be exothermic. So first of all, let's talk about reactions. You probably remember these graphs from first year chemistry. Oh, I didn't mean to do glitter rainbow, but that's okay. We'll go with it. Let's turn it into an easier color to look at. So these hill diagrams tell you about the energy of the system in terms of the reaction. So if we label these as the reactants, and these are the products, and the y-axis is a measure of the potential energy. Notice that for that one, the reactants have a higher energy and the products have a lower energy, which means that the products are more stable. And if you remember from first year chemistry, that nature is trying to go towards stability most of the time. So a lot of times, if you ask why is something happening in nature, it's because the things are trying to become more stable. So this one happens to be favored in nature because the products are more stable. Also, if you notice the energy that it takes to get over that hill, that's called the activation energy. You might remember that. The activation energy tends to be lower for exothermic. If you take a look at endothermic, notice that our activation energy is a whole lot higher, and the products are at a higher energy state than the reactants. So there are other forces that are involved. So sometimes endothermic reactions do happen. So this would be something like a cooling pad. If you're an athlete and you have a sore muscle or something, and you break the seal and it gets really cold, a cold pack, to put on your muscles, that's an endothermic reaction. And you might say, well, why does that even happen if the reactants are more stable than the products? It seems like it wouldn't even happen. But there are other factors that are involved. So sometimes the endothermic reactions can still happen. All right, so that leads us to internal energy, which is equal to the heat plus the work. So if we take both of those factors into account, we can calculate the total internal energy. In terms of heat, we're going to use the MCAT equation from first year chemistry. So for this equation, what you're going to have is three different variables. M is the mass, C is the specific heat, but sometimes they will give you the molar heat capacity. So be real careful with these units. You can see units like joules per gram degree Celsius. You can see joules per mole degree Celsius. So just watch out for the units and make sure that your units match this. So for example, if you're given the first one for specific heat, that's the amount of energy required to make 1 gram of something go up 1 degree. So for example, water takes a lot of energy to make it increase its temperature, but a metal like a frying pan will increase its temperature really easily. So the specific heat is a measure of how easily it changes its temperature. So for this first one, joules per gram degree Celsius, you want the M in the MCAT equation to be grams so that it will cancel this grams. But if they give you these units, the molar heat capacity, instead of grams for M, you actually want it to be in moles so that it will cancel this moles right here. So just watch the units that they give you and just convert all of your numbers so that your units will cancel appropriately. If you get a positive, it means it's endothermic, and negative means it's exothermic. For work, you're going to see W equals the pressure times the change in volume. So a positive W means that work is being done on the system, again, on the balloon itself. Negative means it's done on the surroundings. And when we talk about pressure, we're talking about the external pressure. So again, if you think about a balloon, we're talking about the pressure on the balloon from the outside, not the pressure of the gas inside the balloon. All right, that leads us to enthalpy, and you're going to see this word a whole lot, and it actually is a little bit more complicated than what we teach in first year chemistry. It's the sum of both the internal energy and the pressure volume product of a system. And you're probably like, what is she talking about, pressure volume? Well, Most of the time, we do things at constant pressure. So the pressure of the room is not changing that much when we do experiments. In fact, if you want to change the pressure, you have to have some pretty fancy equipment to make the pressure change at a fast pace. So most of the time, the pressure is not involved. And since this is pressure times volume, if you're multiplying something by 0, then this is just not really going to be involved. So most of the time, we're going to talk about enthalpy in terms of the heat of the system. So the heat of the reaction. And so most of the time, delta H is going to equal Q. And it's going to be the heat of the products minus the heat of the reactants. Now, here's the thing. When you're given a reaction, and you're going to see this a ton, when you're given a reaction like this one I have here, 2A plus 3B yields A2B3, it's going to have a little delta H off to the side with a number and a sign. So that's going to give you a lot of information. It's going to give you information about the heat of this reaction, and that sign tells you whether the heat is going to be leaving or going in. So this tells me it's an exothermic reaction. However, this is really important. If you're zoning out right now, pay attention. It seems like that unit is kilojoules, right? It looks like kilojoules. It's actually not. It's kilojoules per however many moles there are in the question. It's actually a ratio. So what that means is you would have negative 50 kilojoules per, I'm dropping off some of my sig figs just to save time, per 2 moles of A. Or you would have negative 50 kilojoules per 3 moles of B, I'm getting those numbers from the reaction, or negative 50 kilojoules per 1 mole of A2B3. So what you have to do, a lot of times they'll say, if you're going to burn 3 grams of A, how much heat is going to be released? Well, what you have to do first is to get it into moles, because you need to be able to cancel moles, and then you can set up a fence with this ratio. So you would turn it into moles, then you would have moles of A here, however much you're starting with, put that over the 2, put the 50 over the 2 here, and that will allow you to cancel moles. So the whole point is, if you have delta H off to the side, in order to get the amount of energy that they're asking you about, you're going to have to cancel that unit of moles. Even though you can't see moles in the question, it doesn't look like it's per mole, you just have to know that, that it's dependent on the moles from the reaction. All right, there are a few things just to be familiar with. Sometimes you'll see multiple choice questions about these. And the Q of the reaction is equal to delta H if the pressure is constant. And that's the more common one because, again, we don't usually change the pressure of a system while we're doing a reaction. And the Q of the reaction can be equal to delta U if the volume is constant. And that's because there's no work done if you don't have that delta V. Remember, work is negative P delta V. So if there's no change in volume, then there's no work. And so it's just equal to the internal energy, the delta U. If you're starting to get a little confused with all these symbols and equations, I wrote them all down in a summary sheet, and I posted that on Canvas as well. So feel free to use that to help you. All right, one way to calculate delta H, and there's going to be a lot of ways to calculate delta H in this chapter, and you might be thinking, well, how do we know which one? And it's going to be based on the information that they give you in the question. So this is just one way, and you're going to do this several times for this chapter. If they give you a reaction and ask you about the delta H, a lot of times they'll give you the heat of formation of various things in the reaction. And so first of all, delta always means products minus, or the final minus the initial. So in this case, it's going to be the products minus the reactants. And what you're going to do is take the amounts that they give you. So for example, over here, they give us the heat of formation of A2B3. They also gave it to us for B. And so we're going to do the products minus the reactants. But notice that we've got per mole. So you do have to multiply it by the moles in the reaction. So for that first one, we would say we have 1 mole of A2B3. This is from the reaction, times the 35 kilojoules per mole. And that's our product. So we're going to say that amount, products, minus the reactants. So then we're going to add up all the reactants. We have the heat of formation of B, and we have 3 moles from the reaction. So don't forget to multiply. That's coming from the balanced reaction from right here. Multiply the moles in the reaction times the amount they give you. And for your homework, you're going to have to look these values up. There's a table in the back of the book that gives you these values, the heat of formation, which is the energy required to form it at 25 degrees Celsius to make 1 mole of it, or 1 atm if it's a gas. And then normally we would also do 2 moles of A times its thing. But notice there isn't one. And you're going to find that in your problems where you're like, wait, there isn't one in the back of the book, or she didn't give it to me, and that means it's 0. So if it's a pure substance in its pure state, like copper is a solid. So if it's pure copper that's a solid, then it's not going to have a heat of formation because you didn't have to do anything to form it. And so it'll just be 0. So if you feel like you're missing one, then that one is going to be 0. And I'll stop it here and pick it up in the next video.